Hi, everyone. In this lecture, we're going to be talking about chemical quantities within a reaction, calculating amounts of product or reactant for a given chemical reaction. Now, the first concept we need to look at is something called the law of the conservation of mass. And this basically means that in a chemical reaction, we're not creating or destroying matter. Like the Lego example I used last time, we're just rearranging the Legos to make a new set, but we're not creating something from nothing. And so the mass of the reactants has to equal the mass of the products. Okay. So here's an example showing things being weighed out on a scale. If you react silver and sulfur, you can make silver sulfide. If we took 215.8 grams of silver and 32.1 grams of sulfur, we would produce 247.9 grams of silver sulfide. Sorry, that's a typo. Oh, actually, it says sulfide. It's just a little scrunched. There we go. So basically, the mass of the reactants has to equal the mass of the products, is the take-home message here. All right, conservation of mass. Now, when we're reading equations, the coefficients tell us the number of individual molecules, or we could think of it in terms of moles. So, two irons react with three sulfurs to produce one iron sulfide. You can think of this as 2 moles of iron plus 3 moles of sulfur makes 1 mole of iron 2 sulfide. And we can compare the ratio of two different things in a balanced chemical equation. We call this the mole to mole ratio. So if we're looking at iron and sulfur here, there's 2 irons and 3 sulfurs. So we could express that as 2 moles of iron per 3 moles of sulfur, or you could express it the other way around, 3 moles of sulfur for every 2 moles of iron. Or let's say we're comparing iron and iron sulfide. It's implied that there's only one iron sulfide when there's a number given. So we could say that there's 2 moles of iron for every 1 mole of iron sulfide, or 1 mole of iron sulfide for every 2 moles of iron. Or let's say we're comparing sulfur and iron sulfide. Well, that's a 3-to-1 ratio. There's 3 moles of sulfur for every 1 mole of iron sulfide, or 1 mole of iron sulfide for every 3 moles of sulfur. So you can create conversion factors from the coefficients in your balanced chemical equation. Think of this like a recipe. Um, let's say we're making grilled cheese sandwiches, right? You have 2 breads plus 1 cheese equals 1 sandwich, right? It's a recipe. This tells you how many of each thing you need, you know. And so if I told you that there were, 42 slices of bread, how many sandwiches could you make? Well, it's a pretty easy calculation here, but just as an example, right? You use your mole to mole ratio from the balanced equation, right? There's 1 sandwich for every 2 breads. And so you would end up with 21 sandwiches. Simple example, but this is the exact same thing we're doing here with a chemical equation. 2 of these plus 3 of these makes 1 of those. And the ratio comes from the recipe. Okay. Just like the grilled cheese sandwich example. So here's a different equation. 3 hydrogens and 1 nitrogen creates 2 ammonias. What is the multiple ratio of N2 and H2? Well, I see that there's 1 mole of N2 for every 3 moles of H2. And you could express that the other way around. Right? You could write it as 3 moles of H2 over 1 mole of N2. Now, what's the mole ratio of ammonia and H2? Well, there's 2 moles of NH3 for every 3 moles of H2, or you could express it the other way around. 3 moles of H2 for every 2 moles of NH2. Just comparing the coefficients in our balanced chemical equation. Now, here's a practice problem about moles. How many moles of Fe2O3 can be made from 6 moles of oxygen? Well, we are going to start with the given value, 6 moles of oxygen. And then we're going to use our ratio because they're asking us about Fe2O3. So we're going to compare the ratio of Fe2O3 versus oxygen. And it's a 3:2 ratio. So we have a conversion factor here. We want moles of O2 on the bottom so that it cancels. And we want moles of Fe2O3 on top. And so it's a 2:3 ratio. Moles of oxygen cancels. And we end up with 4 moles of Fe2O3. Do another practice. How many moles of iron are needed for the reaction of 12 moles of O2? So let's start with the given value. 12 moles of O2. And we want moles of iron. So we're going to compare the iron and the O2. We want moles of O2 on the bottom. We want moles of iron on top. Looks like there's 4 irons for every 3 oxygens. When we multiply this across, 12 times 4 divided by 3, I think I'm going to get 16.0 moles of iron. Cool. So now that we've compared the mole to mole ratio, let's start looking at mass. So the concept here is compounds have different weights, but the chemical equation, the balanced equations, are based on moles, not mass. And so if we have a certain amount of a starting material or reactant, can we calculate the amount of product? And so to do that, we're going to have to look at molar masses. So the learning goal here is given the mass of grams of a substance, calculate the mass in grams of another substance in the reaction. So the steps are as follows. You have to convert the mass of the first thing into moles using molar mass. Then you have to use your mole to mole ratio. And then you have to convert back to grams using the molar mass of the second thing. So grams of A, molar mass gives you moles of A. And then we use the mole to mole ratio to get moles of B. Then we use the molar mass of B to get grams of B. So here's an example. Suppose we want to determine the mass in grams of NH3 that can be produced from 32 grams of N2 in the following equation. So we are given 32 grams of N2, and we need the grams of NH3. So we're going to start with grams of N2. We're going to go to moles of N2. Then we're going to go to moles of NH3, and then we're going to go to grams of NH3. And so we're going to have 3 conversion factors to do this. First, we need the molar masses of N2 and NH3. So we go to the periodic table. N2 means there's 2 nitrogens. So N2 is going to have a mass of 28.02 grams. NH3, add them all up, you're going to have 17.04 grams. So next thing we need is the mole-to-mole ratio. So from our balanced chemical equation, there's only one N2 and there's 2 NH3s. So you can make your conversion factor there. Next thing we're going to do is set it up. So you start with the grams that were given. And they gave us 32 grams of N2. Then we're going to use our molar mass of N2. We want grams of N2 on the bottom, moles on top. So 1 mole for every 28.02 grams. Grams of N2 cancels. Then we're going to use the mole-to-mole ratio. We want moles of N2 on the bottom and moles of NH3 on top. Moles of N2 cancels. And the third conversion factor we want is the molar mass of NH3, 17.05 grams per mole. Moles of NH3 cancels. We end up with 39 grams of NH3. Grams, molar mass, mole-to-mole ratio, molar mass. Let's do a practice problem. How many grams of O2 are needed to produce 45.8 grams of Fe2O3 according to the following reaction? So they give you the balanced equation, and they give you the amount that you're starting with. So we got to go from grams of Fe2O3 to grams of O2. So first, you got to get the molar masses of iron oxide and oxygen. So O2 is going to be 32 grams. Fe2O3 is going to be 159.7 grams. And then we look at our mole-to-mole ratio. It's a 3 oxygen to 2 iron oxide. Then we set up the problem. So we start with the given grams of iron oxide. We do the molar mass. There's 1 mole of iron oxide for every 159.7 grams. Grams of iron oxide cancels. Then we do our mole-to-mole ratio. Moles of iron oxide on the bottom, moles of oxygen on top. It's a 3-to-2 ratio. And then the last thing is the molar mass of oxygen. 32 grams per mole. Moles of oxygen cancel. And when you multiply everything out on your calculator, you'll end up with 13.8 grams of O2. Let's do a practice problem. I'm going to delete this so we have space, and we'll just try and do it all on one slide here. The reaction between H2 and O2 produces 13.1 grams of water. How many grams of O2 reacted? So we're comparing O2 and water. So we're looking here and here. We need the molar masses. So O2, oxygen is 16, so 2 times 16 is 32 grams per mole. We get this from the periodic table, right? Oxygen is 16. And water, H2O, hydrogen, there's 2, and it's 1.01. and oxygen is 16. We add those up, and I'm going to have 18.02 grams per mole. Once again, you get those values from the periodic table. And then our mole to mole ratio is a 2-to-1. So let's set everything up. Start with the given value here, 13.1 grams of water. 13.1 grams of H2O. We're going to set up our first conversion factor. We want grams of H2O on the bottom, and we want moles of H2O on top. And there is 1 mole of H2O for every 18.02 grams. Grams of H2O cancels. Next conversion factor, we want moles of H2O on the bottom, so it cancels, and we want moles of O2 on top, and it looks like it's a 1-to-2 ratio. Moles of water cancels. And then our last conversion factor is grams of O2. Whoops. We want grams of O2 for moles of O2, and it's 32 grams per mole. And when we multiply all that out, let's see, 15.1 times 32 divided by 15.02 times 2. I get 11.6 grams of oxygen. Let's see if we did it right. Yes, we did. So that concludes the lecture. Just remember, start with the given grams, use molar mass, mole to mole ratio, and then molar mass again. So there'll always be just 3 conversion factors to go from mass of one thing to mass of another. Thanks for watching. I'll see you in the next video.